So I'll be talking today about some work we've been doing in Bristol. This is me, and together with Andrew Hogg, looking at rapid granular chute flows. I'll tell you something about steady solutions and then go on to discuss their linear stability. So our aim is to model the gravity-driven free surface flow of spherical grains down an inclined chute. By looking at the highly agitated, highly energetic regime, we can use a continuum model which is derived from the kinetic theory, which has been adapted to describe inelastic collisions. We characterize the energy loss in the collisions by a single constant coefficient of restitution, which is here denoted by E. And then our continuum equations are familiar from compressible fluid mechanics, except that our equation for conservation of energy includes a term to account for the energy loss in the inelastic collisions. So these equations describe the evolution of our mean field variables, which are the volume fraction, mean flow velocity, and the granular temperature, which is the measure of the agitation in the system. The kinetic theory also provides closures for this system by relating the pressure tensor, the heat flux, and the dissipation to the mean field variables. Here we use the theory of Lunn and co-workers, which gives us a pressure tensor in this Newtonian form, although of course it isn't Newtonian because the viscosity here depends on the volume fraction and the temperature, and those are coupled to the strain rate as well. So then we have an isotropic pressure, a bulk viscosity and a shear viscosity, and for the heat flux we have a modified Fourier law. So all these G functions are some known nonlinear functions of the volume fraction and the coefficient of restitution, but they're sufficiently unpleasant to stop me from writing them. We also need conditions to describe the behavior at boundaries on the flow. At the base boundary, we impose a momentum balance and an energy balance, which gives us these conditions where here M is known as the boundary traction force and D is the energy dissipation in collisions between grains and the boundary. We use the boundary closures of Richman, who takes a kinetic theory averaging approach to find forms for M and D, and his analysis introduces a boundary roughness parameter which depends on the geometry of the boundary, and he also introduces a coefficient of restitution in collisions with the wall, which may be different from the coefficient of restitution in the flow. Finally, at the surface, if we try to demand the free surface conditions of vanishing mass flux, momentum flux, and energy flux, we find that these can only be satisfied in the limit as the distance from the base goes to infinity. So to impose these conditions, we have to impose the equations on the semi-infinite domain. So we call these the asymptotic free surface conditions. An alternative has been proposed by Jenkins and Haynes, who recognise that the kinetic theory is not appropriate in the region of saltating grains where there's no collisions taking place. And they define a surface as the interface between the saltating grains and the collisional bulk. And at that interface, the mean free time between collisions equals the time of a ballistic flight. And then we obtain these conditions, so a condition on the pressure and a condition on the flux of granular temperature. And we notice here that the saltating grains heat the collisional bulk when they collide back with it. So for the interface conditions, the height of the interface remains undetermined at this stage. So we go on now to look for solutions corresponding to steady, fully developed flows. Then all our flow variables become functions only of the distance from the base, and we only have a downslope component of the velocity. And then we can reduce the governing equations to a system of coupled nonlinear ordinary differential equations, which are supplemented by conditions at the base and our choice of either asymptotic conditions or interface conditions for the surface. We need to impose a further condition to obtain a solution, and here we choose to impose a volume flux constraint given by this integral over the flow depth. And if we use the asymptotic conditions, then h equals infinity. So to solve this nonlinear system, we've developed a Map-Chebyshev's pseudospectral method, and that allows us to solve the system efficiently to very high accuracy. And perhaps more importantly, the pseudospectral method can be easily coupled to parametric continuation, which allows us to efficiently find solutions as we vary parameters. Let's take a look at some example solutions. So first, fix in material parameters and fix a chute slope. And we'll look for solutions with volume flux equal to 3. And using parametric continuation, we can find 3 such solutions. So first, for the asymptotic free surface conditions, we have in green a dilute, high temperature, and fast flowing flow. In red, we have a dense, shallow, cold and slow flow, and in blue there's some flow intermediate between these two. If we look at the interface conditions, and each of those solutions has its counterpart, and they look at least similar. So let's take a look at actually just the volume fraction profiles, and in the dotted curves here are with the asymptotic conditions and the solid lines with the interface conditions. So we see that the form of the surface condition only has a very small effect on these flow solutions. We'd like to characterize the solutions using macroscopic depth integrated variables. So here we define the volume holdup as a measure of the mass of material in the flow, and the center of volume as a measure of the flow depth. Then the parametric continuation algorithm can be used to trace the dependence of these variables on the imposed volume flux, and we find there's a region where these 3 solutions are possible, and that occurs for both the asymptotic conditions and the interface conditions, with only a small quantitative difference in the curves. If we look at varying the chute slope by keeping the material parameters fixed, we see that for these gentle slopes, we always have this region where 3 solutions are possible for a fixed volume flux of material. Whereas on the steeper slopes, as we make the slope steeper, we reach a point where there's a change in behavior, and now we have a minimum volume flux for which steady solutions are possible, and above that minimum value we always find 2 solutions for a given volume flux. So let's look now at the stability of these steady solutions. So we're going to assess the linear stability to small perturbations in both downslope and cross-slope directions. And we use a classical normal mode analysis. We'll begin by looking at these 3 example solutions. And from this point, we're using only the asymptotic surface conditions. So first of all, the high temperature steady flow. So here the contours of the growth rate as a function of the wave numbers, and we see there's a region of instability which is elongated along the ky axis, and indeed the most unstable mode here is a purely downslope perturbation from here. This is the corresponding eigenfunction. I'm sure everyone can see exactly what's happening from that. So if we look instead at the local volume flux vectors on top of contours of the volume fraction, we see that this instability results from grains being thrown out of relatively dilute regions and moving into relatively dense regions, which enhances the density contrast. So this perturbation grows. Looking now at the mid-temperature steady flow, the growth rate contours look quite similar, and again the most unstable mode is a purely cross-slope perturbation. If we look at the eigenfunction this time, the striking difference here is that in the cross-slope perturbation velocity component, we've picked up a small non-zero velocity at the base, and that's enough to change the mass transport so that here we have counter-rotating vortices. So for the low temperature steady flow, this time the growth rate contours look different. The most unstable mode this time is a purely downslope perturbation, and the volume flux vectors show there's transport across both relatively dense and relatively dilute regions, but there's a slight preference into relatively dense regions, so the density contrast grows. If we perform the stability analysis for many flows along this macroscopic QH curve, we find there's only a relatively small part corresponding to stable solutions, and that occurs on the mid-temperature branch. And this is a plot of the growth rate contours as we go along this curve, and we have a change from cross-slope instability on the high-temperature branch through the stable solution, and then we come out on the low-temperature branch with downslope perturbations being the most unstable. If we look at change in the angle of inclination, we see that for sufficiently for sufficiently gentle slopes and sufficiently steep slopes, we have no linearly stable solutions. The shaded region here denotes those steady flows which have a density inversion, and the density inversion has been suggested as a cause of the instability, but we see that there's no correlation between steady flows having a density inversion and linear instability. So I'll leave you with the summary and future directions.
Question, please.
Would you identify the downslope perturbations with roll waves?
I'm not sure it's clear from the mass flux vectors that they're roll waves. They're also propagating instabilities as well. So the dense region is moving up the slope. I'm not sure if. I think I would interpret them just as a clustering instability.
Kumar?
Yeah, I mean the extended kinetic theory of Jenkins was formulated because the regular equations predict that the volume fraction increases as the angle of inclination increases.
Mm-hmm.
And that leads to an unsteady, I mean there is no steady state solution in that case.
Yeah, sure.
So what is it that you do differently to get a steady state solution?
So eventually, if you increase the slope sufficiently here, then I can no longer find a steady solution.
So you're at relatively small slope.
Yeah, they're still fairly gentle slopes.
Nick?
Wait.
Okay. Yes.
So the wavelength of your pattern, is it twice the thickness of the?
No, it's much bigger. These are very, very long wavelength instabilities. If I go back, see this one is maybe 500 particle diameters here. It's much, much deeper. Sorry, much longer than the depth of